Hello my dear students, welcome to Learning Chemistry is Easy and Fun. As promised, this is a separate video dealing with the derivation of the radius of the electron or the radius of the orbit taken by an electron according to the Bohr's model of the atom. Lesson 8 we had discussed the Bohr's model of the atom, and we had also tried to explain how Bohr tried to overcome the defects of the Rutherford's model of the atom. Lesson 9 we are starting with the success of the Bohr's model of the atom. Now again and again we are talking about the Bohr's model of the atom. If you are not very clear about this concept, please go back to lesson 7 and 8 where we have dealt with how Bohr came upon to build his or predict his model of the atom in order to overcome the defects which were there in the Rutherford's model of the atom. Before you proceed with this, make sure that you are very thorough with the concept of the Bohr's model of the atom, where we have talked about the quantization of energy as well as the quantization of angular momentum concepts given by Bohr. Some of the successes of Bohr's model were that he was successful in something what we call as quantization of energy. He predicted that an electron in a particular orbit will always be associated with a fixed amount of energy called as quantization of energy. On the basis of that, he was able to predict and he was able to calculate the distance of an electron in an orbit from the nucleus. On the basis of his model, he was also able to explain the spectrum of hydrogen. Now all these things we shall be dealing with in step by step separate videos. This particular video I'm concentrating on the value of Rn. Now this may not be of academic interest to some if you are not dealing really with the derivation and the physics part of it. So you can just ignore it and go on to the other and or just concentrate on the final equation part of it. But if you are very keen on knowing and on understanding the crux of how we derive a formula or how did we come to the final expression regarding the radius of an orbit, the first or the second or the third orbit and so on for an atom like hydrogen, it is better that you go through this derivation, but it is not compulsory. Okay, you can still manage your numericals if you know the final expression, but if you are an avid learner, I would feel that you go through the derivation as well. Now the radius of the electron in any orbit of hydrogen is given by the expression Rn is 0.529 into n square upon Z angstrom units. Now this n stands for the number of the orbit, Z stands for the atomic number of the orbit. Now if I'm talking about a hydrogen atom in the first orbit, that means n is 1, Z is also 1 because the atomic number of hydrogen is 1, in which case Rn comes to 0.529 angstrom units, or what is also called as Bohr's radius in honor of the scientist who has given us this interesting model. This expression is valid for hydrogenic atoms. That means atoms which are like hydrogen with one electron in them. So if I am talking about He positive, that means helium atom which has lost one electron. That means it will have one electron. But the atomic number for this still remains as 2. So Z takes the value 2. N again stays as 1. If I am talking about Li2 positive, again Z is 3. But the N stays as 1. I am talking about the first orbit. For Be3 positive, it has lost 3 electrons. So Z over here is 4. So depending upon what atom you are talking about, you can replace the expression or you can replace the value of the variable accordingly and find out the radius. How have I derived this expression is what has been taken up on the right side of the board. The simple logic that we start with over here is the centripetal force and the Coulombic force. What is centripetal force is when a body moves in a circular path, there's a force acting tangentially, because you know that this body is under acceleration even though it is moving with a constant speed, because the direction of this is changing, because of which what will happen is there is acceleration. The force experienced by this body moving in a circular path is what we call as centripetal force, given by the expression mv square upon r. In the case of a charged body, it helps to balance the Coulombic force. Here I have an electron which is negatively charged. The protons present in the nucleus are positively charged. The simple logic will be that the two will pull each other because they are oppositely charged in nature. But Coulomb gave the law that these two bodies, they will experience a force which is directly proportional to the product of the charges involved and inversely proportional to the square of distance between them. You also know that when we remove the proportionality sign, we introduce a constant over here called as K. Here it is called as the permittivity constant. If you talk about the CGS system of units, K takes the value of 1. If you talk about the SI system of units, this takes the approximate value of 9 into 10 to the power 9 Newton meter square per Coulomb square. Now this is an area of physics where I will not really enter, because then we will be deviating from our topic over here. Because this electron continues to move around the nucleus in a circular orbit, according to Bohr, the two forces are balancing each other. This tries to overcome the defect of the Rutherford's model, wherein the scientists had said and objected that if an electron is moving around the nucleus in a circular path, what will happen is after some time it will lose its energy and it will fall into the nucleus. The radius will go on getting smaller. Bohr said no, it's fixed. The energy of the electron in a particular orbit is fixed, and so is the distance from the nucleus. So mv square upon r is equals to k Ze. Ze is the charge on the protons, because Z stands for the atomic number, into the charge of the electron divided by r square. Now r is the radius of the orbit that we are talking about over here. Secondly, if you remember, we had talked about the quantization of angular momentum, and according to Bohr, only those orbits are possible where the angular momentum is an integral multiple of h upon 2 pi, or mvr is equals to nh upon 2 pi. From here, we will get the value for v as nh upon 2 pi r into m, taking these to the denominator. I get my equation over here, which gives me the value for v. This value of v, we substitute in our equation 1. I have done it step by step. I would feel that you try to do it yourself rather than just copy what is written over here, because that will make the topic interesting as well for you. So mv square we have is equals to k Ze square upon r. Now simplifying, what do we get here? R is n square h square upon 4 pi square me square into the atomic number into the constant, Coulombic constant that we've got. What is the value of r over here? If you see here, I've put the values. H, Planck's constant, mass of the electron, the constant 8.988 into 10 to the power 9. Now if you'd notice, this differs from the value that I have put on the right side of the board, 9 into 10 to the power 9. Now 9 into 10 to the power 9 is taken as an approximation depending upon the level of scientific work that we need to do. Now because I want to find out the value of Rn specifically, I've taken the exact value up to 3 decimal places. So 8.988 into 10 to the power 9 Newton meter square per Coulomb square. Charge of the electron 1.602 into 10 to the power minus 19 coulombs. When we put these values in our expression here, n square h square upon 4 pi square me square into atomic number into k, we get Rn as 5.29 into 10 to the power minus 11 upon z into n square meter. This is a very, very small value, into 10 to the power minus 11 meters, right? So we try to convert it into a more scientific friendly expression, and that is 0.529 into n square upon z angstrom units. Now here I will share something interesting with you. If you take the values of h as like 6.6 into 10 to the power minus 34, mass of the electron is just 9.1, k as 9 into 10 to the power 9, charge of the electron is just 1.6 into 10 to the power minus 19 coulombs. I tried it again and again, and the value comes out as 0.526 angstrom units. So depending upon the number of significant figures that you have taken for each of the values, the Rn value could be 0.526 to 0.529 into 10 n square upon z angstrom units. Now it is up to the third, it is at the third decimal place. So some places you will find the expression as 0.53 angstrom units also as given. That is, the radius of the Bohr's orbit is 0.53 angstrom units, which is taken instead of 0.529, right? So from here we can use the expression in our numericals depending upon what is the atomic number which is taken. You need not bother about it because this is at the third decimal place, and you can try it yourself with the help of the calculations, with the help of this expression. If you've liked the video, please don't forget to subscribe and share it with your friends, because learning is all about sharing, and sharing makes you feel happy. Have a nice day.